Okay, this is a question that I got today from one of the Chem 8 students. I think it also applies to Chem 7. It's an important review topic, so I'm going to post the link in both areas. Anyway, the question was, uh, what is Zeff and how do you calculate it? Well, okay, so here's the first thing. The definition of Zeff is that this represents the amount of charge that is available to pull on the valence electrons. In the example that I have at the top of the whiteboard here, we have the element carbon with the total number of protons. All right, so this would be its atomic number, and um, this represents the electron configuration. And you can see that I've circled the valence and I've circled the core. It's super important that you review and that you understand how to identify the core and how to identify the valence of any element. With that in mind, before I come back to the actual question at hand here, let's just practice this up really fast down here. So here's magnesium. It has an atomic number of 12. Its electron configuration will be 1s2, 2s2, 2p6, 3s2 for a grand total of 12 electrons. All right, I'm going to underline the valence. So you need to review the valences because a lot of students make mistakes and seem to have trouble identifying valence. So anyway, this is the valence of magnesium. And that means that the remaining electrons here are the core. Make sure you can identify the core and the valence of any electrons in the first 4 periods of the periodic table. Now, the Zeff for this is going to be the atomic number minus the core electrons. And you can see that in the core we have a total of 10. So the amount of charge that's actually operating on or pulling on the outer valence of magnesium is +2, because the core electrons essentially shield the valence from the protons that are in the nucleus of the atom. In the middle of my slide is another example. And here what we're doing is we're calculating the Zephyr carbon. So again, to review, it is the atomic number minus the core electrons. And the Zephyr carbon is going to be the atomic number shown here, which is 6, minus the core electrons. So going back to the top of the slide, we see that the core for carbon is just 2 electrons, and then the outer valence was 2s2, 2p2, a grand total of 4 that are in the valence. All right, so the Zephyr carbon is going to be the atomic number 6 minus the 2 electrons that come from the core, and that gives us the amount of charge that is pulling on the valence, which is the Zeff, at 4. Notice that the Zeff for main group elements is equal to the group number. So the group number actually has a couple different meanings, right? One of those meanings is the number of valence electrons. So there's 4 valence electrons in carbon. The second meaning is that it gives you the Zeff. And Zeff is important because this is what is exerting the force on the valence electrons. And the valence electrons are what determine the size of that particular atom. So the harder you're pulling on the valence, the smaller that element is. All right, now let's shift to the next screen. All right, so now what I'm going to do is run 2 examples on ions. So we started out with a question on, okay, what is Zeff? And then the next question from this Chem 8 person was, how do you apply Zeff, or how do you figure out the size of the ions relative to a neutral element? So first we're going to start talking about the cations. And the first rule is that your cations are always smaller than the neutral element. And what I'm showing you here is the reason why. All right, there's actually 2 reasons. One of them is that the Zeff for the cation is always a higher value than it is for the neutral element. And the second thing is that once you form the cation itself has a new valence, which is actually in a lower energy level. So if we just run through the details of this now, if we start out and we determine the electron configuration in the Zeff for the neutral sodium, for example, the configuration is shown here. There's a total of 11 electrons. The valence is circled here. It's 3s1, right? And the remaining electrons that are interior to this, between the valence and where the protons are, right? There's 11 protons in here. This represents the core electrons. So to find the Zeff, it's going to be the atomic number, which is here, right? This is atomic number, minus the core electrons, which are here. And so we see that the Zeff for neutral sodium is actually +1. Now, when we look at the same issue, except now for the cation, you need to remember that the cation is lost an electron, so it actually only has 10 electrons in it versus 11 for the neutral element. So when we write the configuration for that, it's going to be 1s2, 2s2, 2p6. We have shifted to a lower energy level in the cation. So that means that the valence electrons are actually closer to the protons. Secondly, when we calculate the Zeff, again, this would be the atomic number for the element. That hasn't changed. Minus the core. But now we have a new core because we have a new valence. We ditched this 3s1 electron here. It went away, right? It was reacted with something and this electron was transferred. So the new core is only 2 electrons, which means that now the Zeff is actually +9. All right. It's important to see or compare this to the neutral element because the amount of charge pulling on the valence of the cation is 9 times higher than the amount of charge that is pulling on the valence of the neutral element in the case of sodium. It's a ratio of 9 to 1. This is one of the primary reasons. It's at least half the reason. It's at least half the reason why the cation is going to be smaller than the neutral element. You have both of these factors. The Zeff is significantly higher in the cation operating on the valence, and the new valence is in a lower energy level, so it's closer to the protons, and so the cation, in terms of its size, is significantly smaller than the neutral element. I'm going to say that one more time. The cation is significantly smaller than the neutral element because the Zeff is higher and the valence is in a lower energy level. Okay, now let's go to the anion. So remember the anions, well, the rule is the anions are always bigger than the neutral element. And remember that your anions have gained electrons. They've gained at least 1 electron. And the example that I'm going to use here is chloride, which has gained an additional single electron versus the neutral element. Now, you got to understand, and I'm addressing the memorizers here, that anion is bigger than the neutral element for completely different reasons than the argument we just had with the cations, right? It's completely different. So let's just run through this. First things first, what I've done here is provided the electron configuration for the neutral element. And for chlorine, there are 17 electrons, so the outer valence is 3s2, 3p5, right? This is the valence. Three s2, 3p5, which makes this guy over here the core, of which there are 6 and 2 is 8 and 2 is 10 electrons in the core. So to calculate the Zeff for this, it's going to be the atomic number, which is 17, minus the core, which is 10, for a grand total of +7. Now, we're going to go directly to the anion because it's super important for you to see this. We've added a single electron. Where did it come? It went into n equal 3, which is exactly the same energy level as the valence of the neutral element. So we did not change the outer valence. We did not change the energy level of the outer valence. It's the same. So there's no distance difference in regard to the valence of the anion compared to the valence of the neutral element. Now, when we calculate the Zeff, you see the calculation is identical. The core did not change. Here's the core, and here's the valence. Both the valence, the number of electrons in the valence is different, but the N number did not change. That extra electron came into exactly the same energy level. Yet the Zeff, you can see when we calculate it, is the same as the neutral element. Same. +7 and +7. The same number. So, what's going on with the anion? Why is it bigger than the neutral element? So, here are the facts. First is there is no change in the energy level. So, that can't be influencing anything. Also, notice the Zeff doesn't change either. So, it can't be influencing the size. So, this business here, no change or no influence, which means that this last thing here is where all the business is. All of the business is right here, and is in particular characteristic of anions. So the reason why the anion is bigger is because the electrons are all paired up, and this causes repulsion, and the valence therefore expands, and the anion is bigger. And it's bigger for this reason. I'm just going to abbreviate that. So once again, I'm going to say this over again. The singular reason why the anion is bigger is because the electrons are paired. This causes repulsion. The valence expands, and therefore the anion is bigger. Okay, and with that, I'm going to close the video.